So we are Ant. Dynastream is the owner of the Ant technology, and Ant has been in the marketplace for 10 years this month. And it will now be running awful close to 100 million deployed devices with our recent announcement with the Samsung Note 3 adopting Ant as a key structure for their S-Health platform. So we have now added 3 new cell phones, including the Note, the 2 new Sony products in the market, the Z1 and the Z Ultra, and many more still. The ultra-low power wireless market has changed dramatically in the last 10 years, and the cell phone has become a predominant hub for many applications. So we want to give you the assurance that long-term that Ant will be deployed in virtually all cell phones, perhaps except for Apple. So I'm going to start now. Hopefully I can... Okay, so what I wanted to show you first was that Ant is very much a easy to use but very flexible protocol that is built into the Nordic NRF 51, the NRF 24AP2 family, and the NRF 24AP1 family. But we have found in the years that successful designs quite often need to get some help. So we've provided a lot of development resources through our website at www.thisisant.com. We very much would expect that your electronic contacts would be your first point of contact. Many of them have had a lot of experience with Ant, and for those that haven't, I'd be happy to lend a hand. So we do an extensive amount of support and application, almost consulting. All of this is for free. So Ant is a ultra-low power protocol stack that we invented for our own uses. Subsequently, we built it as a product for third-party use with our partnership with Nordic Semiconductor in 2004. So since then, we've been able to provide a variety of different products that allow for self-synchronizing and adaptable network capabilities. All of the networks that you would build with Ant are scalable and extensible. You can take your existing products and add features and make them ad hoc or make them asynchronous, or all sorts of new features that have been added that we'll go through in a few minutes. And one of the biggest features about Ant, it is symmetric, and that means that both sides of your link are the same device. You don't have to have a router or a configurator at the hub and then end devices or routers in between. You have the same SKU running the receiver as you do for the transmitter, and in any of the network topologies, they're supported always by the same device. So it makes product development very easy. So Ant Plus, many of you may have heard, our success has been in the sport and fitness world, and now with Samsung's S-Health and many other opportunities out there, we're becoming a strong standard within the consumer health environment. So what Ant Plus is the definition of how the devices operate in a network and how they perform in an application. So we created a set of device profiles that operate on top of the Ant protocol, which we manage under a common network key that's shared by all of the Ant Plus members. It gives you not only true interoperability, but it gives you interchangeability. In other words, you can, as a consumer, buy a device that is labeled with an Ant Plus logo and drop it into replace another device that you had purchased previously, or to add new devices to your product. So it's a value that we add with Ant. If you're in that vertical market, you'll find that it's pretty well the de facto standard. If you're not in a vertical market or not in a interoperable market space, you don't need to use ANT+. You can use any of the ANT+ definitions you like and just use your own network key or the public network key. We do have an alliance of substantially, I think, 355 as of this morning members with well over 5,000 adopters. So we compete quite healthily with Bluetooth. Although we have fewer adopters, we have more paying members than Bluetooth does. Bluetooth has, from what I've been told in the last meetings that we had, just in the high 200s. So we're still a very strong product out there. We're pleased to see that Bluetooth Low Energy has entered the marketplace because it has brought us a lot of opportunities in the more complex network world of home automation, process control, asset tracking, things where a simple beacon and a point-to-point connection is enough. And the brand of ANT+ that you'll see out there, you'll see in cycling as the predominant choice, running fitness equipment, and now with Samsung and their S-Health, soon to be in the consumer health with blood pressure, weight scales, glucometers, and other fitness devices connecting. So we'll talk a little bit about what ANT is. ANT is really an interface layer between an application that you'll develop and the hardware that has been provided by Nordic Semiconductor. So you'll see in the diagram the NRF51, the serial interface inside of there is because of the SoC, is not abstracted as a separate layer. And the AP2 and the USBs that are available as network processor devices require a serial interface layer that is developed by yourselves along with the libraries that we provide. So it's a common message protocol and it's supported by serial commands for the network processors, as I mentioned, and also libraries for the system on chip, the PC environment, and an extensive amount of libraries for Android. So you are asked to configure a channel in whatever method you would want using those standards that are there. You can send and receive messages using a variety of different topologies, and you get event notifications from ANT to your application to let you know the status of your connection. And every connection attempt that you make, every transfer of data, you have a nice quiet in the background event notification. So it takes very little work for you to develop the network, and you can spend 90% of your time working on your application, what makes you differentiated in the marketplace. So ANT channels. You can see the diagram. We have a master and a slave. In the ANT world, master and slave means something slightly different. The master in our world is the transmitter. It defines the channel. You may have a device with 8 separate channels. Each of those channels is completely unique and can be a master or a slave if need be. It's the logical link between the two nodes. It's isochronous, meaning that it does allow you to vary in time between messages dependent upon synchronous connection challenges like RF noise or coexistence issues. That's all managed by the ANT protocol, so you need not worry yourself about others in the neighborhood. ANT will take care of that. And it's built of a bunch of building blocks. So you can define what your network looks like with a drawing and then decide which of the channel options is going to best suit your application. So we have bidirectional or unidirectional connections. And is traditionally a bidirectional connection, but it can be put into a single direction, just like a simple beacon for power consumption. It is synchronous or asynchronous. That's an addition that we've had over the last 3 years or so, and it's proven to be very successful to expand the number of use cases that ANT can address. and we have a multi-drop capability, which is called a shared channel. These will all be explained in more detail later. The messages you have available are broadcast, simple broadcast with much like any beacon that you would see out there. We have an acknowledged message, which is an automated broadcast that is waiting for an event message to come back before it proceeds. And we have a multi-packet data transfer methodology called burst. So this is what an ANT connection looks like. You have the red nodes on the line are your transmissions. You can monitor and change the power of each of the output power of each of the messages. You define the distance between those as the channel period. Each of those red nodes is really about 150 microseconds of radial on time. So you can see that there's probably going to be a very large amount of dead airspace, which gives you the battery consumption numbers that ANT is so famous for. You define each of the transmissions with a network key, a channel ID. You choose an RF frequency that makes sense for your environment, and then you attach 8 bytes of data. You can see the blue node that's on there. That is a receive window that's opened automatically upon a transmission. That allows coexistence to be managed by ANT. So in other words, after a transmission, ANT will listen to see if there's any other transmissions in that space, which will allow it to either continue on at that exact same channel period or slightly modify the timing to move away from any other channels or any other noise that's in that time space. So this is all managed by the protocol. This is not something that you have to spend a lot of time on. So on the receive, you'll end up having, or I should say on the master, every time you send a transmit, you'll see an event message come back. So you'll know that you had a TX. So your application will know that the message was sent. In the case of a broadcast, you don't expect to see anything back. In the case of acknowledgement, you would see an ACK come back as an event, and in a burst, you would have a request to send the next packet. This is what you would see typically in the code that you would develop. We have reference designs and code examples and available C code. All of our code has been developed originally around the MSP 430 because of the network protocol requirement, but now with the NRF 51, we'll be making all of the code available in NRF 51 M0 C code. So slave endpoint basically mirrors the transmission that's being sent in frequency. It should and it will use the same network key, and you will look for a channel ID in order to start the data pairing, and then you would either use the period that's been determined, the channel period, which is the number of messages per second, or you'd use a multiple of that. For example, in the real world, the ANT Plus Heartstrap uses a 4 hertz channel period, and some receivers, like watches, want to save power. So when they go to search, they're searching a channel period that's a multiple of 4. So they may search at 2 or at 1 hertz. The amount of time it takes to find the device is substantially longer in milliseconds, but it's a much lower power consumption. So as you can see by the yellow nodes on the graph, those are the search windows. There's a 10% duty cycle. That is a patent that is built into ANT, and it allows you to be able to get a indication after a specific period of time that you have not made a connection, or you will get a message when you do make a connection. So again, those are the event messages I was talking about earlier. So you'll see the devices line up. You'll see a broadcast and an RX and a TX messaging coming by. You'll see how the the receive window aligns up with the transmit window, and then any acknowledgement sent back on the bottom line there, we have the red node is lined up with a receive window on the master side. You can transmit an acknowledgement from the slave to the master or from the master to the slave. So it's a fully bidirectional capability. And again, an example of the simplicity of the code that you would use in order to be able to manage this in your application. Okay, once you've made that RF connection, now you have to go through an actual decision point as to who you want to connect to and whether you want to secure that connection. So there's a variety of different pairing methodologies that you can use with ANT. You can do it manually. You can choose a wildcard, which means that when you're opening up your receive, that you look for any of the device IDs or any of the device types in the neighborhood, or any of those pieces, whether it be the device type, the device ID, or the transmission type. You can lock down with a number that you know already. You would use isolation, where you have a lot of nodes in the same area. So think of a peloton in a cycling race. When you're going to change tires, you'll have 4 or 5 riders all at the same time trying to repair their power sensors that are on the rear wheels. So in the olden days, you would have to take the bike away from the other bikes to isolate the two transmission and receptions in order to be able to limit the number of bad messages you would get for pairing. But now we use a proximity search for that. So you can have 30 or 40 bikes all in the same vicinity, and you'll have a distance of maybe 5 centimeters or 10 centimeters between the meter and the head display in order to be able to pair. We'll talk a bit more about these in the next couple of slides. I hope everybody understands what pairing means. That is really the association, the hard linking of the two devices. It's an early decision point that you make before you start to transfer data. So again, the data messages are fully bidirectional, and the 3 that we discussed earlier are broadcast, acknowledged, and burst. So no acknowledgement is required or asked for on broadcast. It's really the default for the master endpoint. It's the lowest possible power consumption if you used a transmit-only channel. Be aware that a transmit-only channel, while about half the power consumption of a standard transmit, does not open a receive window. So it would be used only in areas where you had very little worries about coexistence. But it does perform substantially better from a power consumption point of view. You send 8 bytes per message period, and it's really suited for sensor applications where any data loss is really not a concern. A temperature sensor would be a good idea. The temperature doesn't vary that often. If you lose one of the messages for whatever reason, it's not going to affect your application. And then most of the N+ sensors use a broadcast messages. Okay, acknowledged, again, you can see with the A's onto there that you've opened up a transmit channel and you've established that you are sending an acknowledged message, which will require the receiver to automatically provide an acknowledgement back. There's no management at the application level, but you do receive fails or success event messages back, so you will have to manage those in your application. And you can see that if you start a acknowledgement in the slave side, then your transmitter will have to open up a transmit again to send back the acknowledge. So there's a little bit more airtime required, so therefore slightly more amount of power consumption. But again, we're not talking a large amount, we're talking just microamps. Okay, and the burst we mentioned before, it's when you have more than 8 bytes of data that you want to establish a connection for. So you would pick a channel period And then on the next instance of that channel messaging, you would start to send all of the data that you had loaded. Each of the bytes is transferred with an acknowledgement. So byte number 1's acknowledgement will need to be received before byte number 2 will be allowed to transmit. Each of the bytes is numbered, so you will get a indication on the application side as to which byte you're looking for inside your application. That will allow, or each packet, I should say, and so that will allow you to be able to reconstruct a larger stream if it gets interrupted in the middle, or if somehow your application jumbles up the packets as they come through. So you will see about 60 kilobits per second with the new NRF51. That's substantial when you consider the amount of data that you typically have in a small application that's using a coin cell battery. So we've added some new features to the NRF51. So for those of you that are familiar with ANT, you'll see some new tools that will make a lot of the things you had to do at the application layer more automated inside the protocol. So that's supported by both the NRF51 IC or any of the modules available, and it's also supported by the new mini USB that's available, the ANT USB-M. It has a fast burst, that's where the 60 kilobits per second. It has an auto baud rate capability, so it allows you to be able to manage the 60 kilobits per second over a larger number of serial communication options. It has AES-128 encryption built in, so you can choose a single channel of AES-128 encryption. It allows you to filter and buffer those event messages we've been talking about. So if you have a lot of transmissions that you don't really care about the messages coming back, you can buffer them and take out some of them, or you can store them for future reference. It's good for debugging, and then once you get into a regular production mode, most of the time you're not really worried about the event messages, so you can cut down on your application overhead by just filtering the ones you don't care about out. We've built in RSSI, finally, so you have a very good quality RSSI, which is also built into the protocol in the event messages and in the serial protocol. We have a application flash space. There's 500 bytes of flash on the new USB-M, which allows you to put more identification about your product and any rev and configuration requirements. There's a much faster search for, especially on the higher powered receiver side of things. Typically, you start an asynchronous search, as we saw before with the yellow nodes. The fast search will just start a search immediately and not care about the channel period, and quite often will find your transmit in about a tenth of the time. And we've added the ability to put more network keys up from 3 in the AP2 to 8 in the NRF51. Not many applications use that, but when you have a more complex receiver that is talking to a variety, like a home health hub, for example, of different networks, you'd want to have more network keys for private and public networks. So here's how you take the various different broadcast messages and styles of ANT communication and turn them into usable channel configurations that will help you with your application. So a typical one-to-one connection, which is completely independent. The NRF51 has 8 independent channel capacity. The shared channel, which is that pulled multi-drop that I discussed earlier. Some continuous and background scanning, which allow you to be able to make an asynchronous connection and severely improve the amount of power consumption you require on the transmitter. And also, we'd also talk about the file share, which is how you'd be able to store data on a transmitter and then ubiquitously connect with the receiver and transfer these across in a very secure method. So again, independent means that you have a separate master and slave connection for each channel that you open up. The coexistence is managed per channel, quite often used for point of purchase for asset tracking, sports monitoring, any automation, and process control. So this is what an independent channel will look like. You'll have a master at the top. Again, the master is the transmitter. You'll have a variety of slaves out there, and they will all be able to listen to that information because it is purely a broadcast. There's no handshaking required to connect. You can just listen in, and as long as you match the ID of the device, you'll be able to listen to its data. So that is used in a sports world where you have, say, a foot pod, a pedometer, and a heart strap that you're wearing when you're out doing your exercise. You'll have a sport watch that you can look at very easily during your exercise. You may have a cell phone that's important to you to collect data and graph the data, which would be probably in your pack or in your pocket or on a strap on your arm. And if you're doing extreme exercise like triathlons, quite often you'll have a heads-up display that you'll use, so you don't have to worry about a watch or a bike computer being your focus while you're exercising. You can just see the data in front of you. There's a few of those in the market now. So really you've got the same pieces of data coming from the sensors displayed on all three displays. Just so you understand, if you're not familiar already, that is impossible with Bluetooth Low Energy. So if your application isn't sport, but you need to have multiple independent connections between a transmitter and multiple displays, ANT is your best selection. Okay. Again, we've got a device that is being controlled by multiple controls. In this case, this is the Verb from Garmin. It's an action camera. You will have your cycle computer on your handlebars, and you will see the results of the battery life that you've got on your device. You can turn it on and off. The device would maybe strapped to your helmet as you're cycling along. Again, you'll have that cell phone that's stored away in a safe place that you will be seeing your data on later, but you'll be able to control should you ever need to have a little bit more visibility from a display point of view. And you'll also have a remote control, perhaps, it's sitting on the handlebars. So those are all currently available. These products are all in the marketplace now and are quite successful. The variety of control mechanisms really makes the camera a much more usable tool, and it saves a lot on battery life. Instead of recording the stuff you don't need, you only record the stuff you do need. And more cameras are adding ANT as we come along. So there's 3 cameras in the market now. Okay, so this is that multi-drop pulled channel I talked about before. So this is used where you have many more connections than just the 8 independent connections that you want. It's used quite often in automation and process control. It's a connected, using a handshaking methodology, so the devices are always part of a network. They're not just I'll transmit my data when I need to. So it provides you with the security that you've got a link with all of your connections out there. You have an address that you put into the payload, which could be either 1 or 2 bytes, which allows you to be able to connect up to 65,000 devices in either a uni or a bidirectional method. So you can get an acknowledged back from each of the transmissions that you send out. That will give you a really good chance, especially in a process control, to know that you still had a good quality connection and that your receiver has received the information that you're sending. So this is a one-to-many use case or many-to-one. So either way you want to configure it, it gives you a chance to choose your power consumption versus latency. This, again, is your channel periods. Typically on a shared channel will be as low as half a hertz, so once every 2 seconds. And you have to multiply the number of nodes by the channel period to know the rotational time. So if you have 20 nodes on the shared channel, when you have 2 seconds between each one, it will take a maximum of 40 seconds for each node to report back if you pull each one separately. So this is what a shared channel will look like. As you can see on the red nodes onto there, the 0 is recognized by all of the slaves. That's the address that you would put in if you wanted to turn all of the lights on, for example, or all of the lights off. If you want to send a message to every single node on the shared channel, you use an address 0. There's no bidirectional capability on that. It's purely a control methodology. If you wanted a communication back, you would put the specific address. Slave 1 only listens to the 1 address, slave 2 to the 2 address, 3, and so on. So here's an example of a demonstration that we've done, and there's a YouTube presentation of this on our website. This is allowing a cell phone or a remote control or a PC terminal to be able to control battery-operated puck lighting. If you go and buy the pucks, say at Costco or at Aldi's or Lidl or any of those places that sell these consumer products, quite often you have to push each one to turn them on. If you have, say, a display in your house with your trophies from your football prowess or maybe in Canada or hockey prowess, you'd have to turn them all off and all on manually. It becomes a little bit of a challenge. Now you can make a connection with them using an application to turn them all on. And again, you would send a channel 0 onto that. You can see all the lights are on. You can turn them off again using that same channel 0 address, or address, I shouldn't say channel. You can turn individual lights on. Again, there's light number 1 going on because the address has been sent as 1, as 2, as 3. And again, you can turn them all back off again. So this is a really simple way to effectively manage products or devices within a room, within a facility that's, again, line of sight. You probably have with the NRF-51 at 4 dB, 100 meters of line of sight. You can group them. In this case, we've decided to take only 3 of the 6 lights and turn them on, and that is through the auto shared channel definition, allowing you to be able to put a sub-address of zones. There's up to 16 zones that you can put. So it allows you to be able to, say, manage the lights inside of your bedroom. Now we're just turning the lights on and off beside the bed rather than turning all the lights in the bedroom on and off. So again, auto shared channel is a very simple and easy way to perform these types of assured connections. A continuous scanning mode, this isn't a channel because it uses 100% of the receiver. It's completely asynchronous. There is no pairing required. You're just purely connecting to any of the transmitters in the environment. Would be good for activity monitoring or access control, where you have hundreds of people coming by a connection point. There's no determined time they're going to come by, so you want to listen and gather their information, take the data that they have stored on their device, whether it be a single packet or a burst of multiple packets, say as an activity monitor, and it's extremely low latency. There is virtually no time delay between the time the transmitter sends its information and the time your application sees the information. It is a higher power consumption of the receiver. You're probably looking at an average of about 17 milliamps. So it's really designed for something like a USB port or something that's plugged into the wall. But it does give you the flexibility of completing a completely asynchronous connection. We've estimated at 1 hertz transmitters of approximately 300 devices that can be connected simultaneously. Again, because of that coexistence, those transmitters are not transmitting on top of each other. Before they transmit, they listen and make sure there's no one in their space. So again, those 300 1 hertz transmitters will line up themselves behind each other, so you get very little overlapping and collisions, which is really hard to manage in a protocol like Bluetooth, where you have to create your search mechanisms yourself. So there's no finite number, but estimates are as little as 10 will cause collisions in a Bluetooth network. So this is what continuous scanning looks like. I'm hoping you can see it a bit better on your screen. Your slave on the bottom is always on, and at any period your masters are sending a piece of information. They are received, and the data is transmitted through into the application. So again, you've got full identification of the device from the channel ID plus the 8 bytes of data. So you can respond back when you feel you need to respond back to a specific device, and because it has a listening channel that is automatically put on after a transmit, you'll be able to send back an acknowledgement or a full packet of data. Again, this is all automated by the protocol. So a good example is the easy button. You want to turn something on and off. You have no idea when that button is going to be pushed, and you have a device that's sitting there listening to multiple buttons. So very good for process control, activity monitoring, access control, anything where you have no idea of what's coming into range and who it is, but you want to talk to it anyways. Okay, and sometimes you may want to have existing independent channels alongside a synchronous or an asynchronous scanning method. So we've made a background scanning channel. What it does is it performs that same scan in more of a search duty cycle. So it's much lower power, probably in the 2.5 to 3 milliamps of average current, but it allows you to be able to have an independent connection. If you think of a bike computer, for example, you have a heart rate connected. In the background, you may be adding a speed and cadence sensor or a power meter or something else of need, and you don't know what that is. You could open up this background scan while you're getting started before you start your ride, and it would search for all of the devices and provide the application on the device the ability to be able to make a hard pairing with that and continue on. If you had one computer and four different sets of sensors, this would be the easiest way to manage that. So it balances power with the number of messages you get. Again, that's that same ability to be able to connect to hundreds of devices. But again, you're going to miss a few messages here or there because the overlap of the existing channel may be at the same period as that asynchronous transmit was coming from the other device. So you do have to manage that in the application. So this is what it looks like. The scan is much more of a duty cycle, and you will see that the vast majority of the messages are received with very little overhead by the application. You can have the same slave running in the background, and you'll have an acknowledgement of messages. So you can see, you can pick those up, and the masters will be continuing to communicate while your slave is synchronized to be able to connect with that, say, heart rate. In the meantime, in between those messages, you're listening for other products that may be in the environment. So you have multiple connections listening for heart rates and for asynchronous devices in this. So that could be in a gym environment where multiple people are coming by, and you also have some devices that are controlling the application or the machines in the environment. So I mentioned ANTFS earlier. That is the file share. That's what ANTFS stands for. It's a session-based transport mechanism. It's really a state machine that allows you to be able to use a beacon from a receiver, connect with the beacon when you need to on the transmitting device, and then going through an authentication process before you're allowed to transmit data. If you think of a portable blood pressure meter that you would carry with you, take your blood pressure or blood sugar measurements 5-10 times a day, and when you get back to your house, the beacon is picked up, and then you go through this secure authentication, and then once you've proven that you deserve to connect, you'll transfer all of the data that you collected during the day in a big file dump. So you have 3 different layers of communication. You have your link layer, which is a fairly automated process. Your authentication process is a choice of 3 different levels of just pass-through, a pairing mechanism that's initiated by the user. You push a button in order to be able to connect, or a full secure connection using a hash value in between to make a unique connection between those 2 devices. And then you move on to a transport layer, which is when you start to transfer your data. So file transfers between sensors, that's a sensor is a continuous glucose monitor from Dexcom. It's collecting data and storing that data every 5 minutes. It gives your blood sugar information. And when you get home, there's a health hub there from Qualcomm Life that will connect the data, upload all of that data into their cloud, and make it available to your medical application. So we do have a power estimator. I tried to link the demo this morning. I wasn't able to do it. If you go to our website on thisisant.com, go under the developer section, you'll see Power Estimator. And it's a tool that allows you to be able to take all of the channel configurations we've talked about earlier, and the message rates and your data message types, and plug them into here, and what will come out is, after you've defined what type of a battery and duty cycle that you want to use it, you'll get a battery life indication. So when we talk about that shared channel, for example, at 12 hertz, which makes a lot of sense for a theoretical zero latency home automation environment, you're consuming at that beacon, that temperature sensor, for example, about 241 microamps of average current. So that's 12 messages a second, 24 hours a day, will give you about 240 days on a AA battery. So it's very, very, very efficient. But you can choose and measure your own power quite easily on there, and it's quite accurate. Okay, so now we're going to take the channel options. It looks like our timing is getting very close to running out, but I'm going to quicken this up very quickly. So the channel options you have are varied, as you can see by the different topologies. So smartphone accessories these are kind of application areas where you may or may not be interested in, but you can take these as parallels to something you might be interested in. So this is an example of a star network. You've got the main hub, which is the smartphone, and a variety of different accessories you're going to connect to it. Not just one, but you can connect up to 8 independent channels on here. So it can also be a coin cell device. You could use it on a watch because it's very frugal. You could make it on a non-plugged-in adapter that you would put on the wall in a home automation environment, or a process control. You're not limited to a high-powered display by any means. So this is an example of a more complex star. So this is a spin-byte console that has a power and a speed connection. It also has a watch connection and a heart rate connection. The power and the speed devices have to talk to each other in order to calculate the right value. So you're talking sensor to sensor and also sensor to hub. And again, the hub is talking to the watch back and forth for configuration data and real-time storage of your actual generated data, and the watch is also connecting to the heart rate. So you'll be able to see on both of your display devices the culmination of all these calculations. Impossible to do with Bluetooth Low Energy, by the way. Heads-up displays, again, you've got connected stars, so you've got multiple displays looking at the similar data. And in this case, you've got the cell phone transmitting information to the heads-up display perhaps controlling the cell phone. You could use it for audio control if you would like, just by tapping the brim. In this case, this is a German product from OScience, and a bunch of sensors around your bicycle. So you can actually now, with the NRF 51922 that's soon to be available, have ANT channels to your sensors, to the hub, and then the hub, maybe the heads-up display, makes a Bluetooth low energy connection on that same chip back to a cell phone. So you become a bridge between the display or even the heart rate. There's a heart rate out now that is the hub for the ANT Plus sensors and a BLE connection without having to have a display. So that, again, not something that Bluetooth can do on its own. We recognize that Apple is a very important part of the ecosystem out there. We didn't want to leave them out, so we created a chip that would do both on a continuous basis. So you don't have to start and stop an ANT channel in order to communicate with Bluetooth. You can do them simultaneously. So if you wanted to extend data, you have the ability to be able to create relays with ANT. So you have a master on one side, a slave on the other. So what comes in channel 0 goes out channel 1. And you can also have independent channels connecting to either other independent networks or more linked shared channels. So you can create a really nice ad hoc network capability by using this. We do have an application level reference code available for this. Again, it's MSP430C code. It's on our website. Temperature sensors, home automation. You've got temperature sensors connecting in rooms or in areas and funneling that data back through a relay to a longer distance link to the main temperature thermostat around the furnace or whatever. Very capable of that. The practical mesh of taking the star concept and having shared channels on the ends of the star nodes is very viable for each of those clusters out there. On a shared channel would be a different room. Very simple way to manage a complex network. So there's your typical home outlook. You've got shared channels within rooms. Those are independent of each other. If you make another star or a shared channel around the outside, you can now link them all back to one decision point. Therefore, you can create a very inexpensive battery-operated. All these nodes are coin cell battery-operated deployment of a home automation. Dispenser control, washrooms, especially in large buildings, they all have dispensers. Each of those dispensers needs to be filled. The time and energy to go and fill them without knowing what's in them costs a lot of money in labor. If you had each of those linked together on a shared channel, you could walk by the washroom with your smartphone, interrogate the washroom, and find out if there's anything that needs to be filled, whether it's soap or deodorant or toilet paper or whatever you want. So it's a real application. Some companies in Asia are doing this now. Group monitoring, each of those pedometers, for example, is connected through an ANT to Wi-Fi bridge, that WASP in the top right-hand corner. Again, 160 or so users have been tested on this with about a 10K file of data they've collected over the last 24 hours. It allows you to be able to have multiple users walk into a doorway, connect with the receiver, go through that ANT-FS state machine, and then download the data they've collected, all without having to push a button. Again, hundreds of devices can do this at the same time. There are a lot of limitations to our competitor because of the broadcast overlap, so you'll probably see maybe in the tens of units. Group monitoring, this is a picture of a spin class that's in Los Angeles. You've got 80 bikes basically all communicating at the same time. Each one has 3 sensors on it, so that's 320 nodes all coexisting at the same time. If you start one of these classes with one heart rate missing, the class is ruined. In every case that this test happened, this is a customer test, they all started simultaneously, never had any crosstalk. Asset tracking, a warehouse with a scanner, a handheld scanner. You're not tracking where the devices are put on the shelf. You're tracking where the scanner is gone. So simple little beacons that are placed throughout the warehouse. The scanner goes by the beacon, gets its location, and transfers that information via the Wi-Fi connection it's using to communicate with the dispatcher in the middle. So that allows the dispatcher to know where the forklift is and where the individuals are inside the warehouse. You can use that for a variety of different methodologies in asset. As a first responder tracking, an application we have in the UK, beacons inside of each of the rooms and the floors allows the firefighter to be able to connect to the beacon to improve the accuracy of this foot-mounted inertial tracking system. Process monitoring allows a product to start off in a blank stage of inventory, go through multiple process steps, connect with the devices that are on the process. This in case, for example, a filling application. As you add multiple steps to the product, the tag that's on the product will collect that information, and you distinguish the hundreds of tags by using proximity. Again, multiple tags in the environment, hundreds of them can coexist at the same time. So this is a real strong point for ANT. Process monitoring, so you have hundreds of tags around a listening device, and using proximity, you can hone in only on the tag that's the closest. So only on the tag that's come into the filling station, for example. Information terminals at point of purchase. We use these at our annual symposium, so all of the attendees get a little beacon that's a commercially available product, and it allows them to be able to see what their status in the events throughout the symposium and who their teammates are just by walking up to a PC terminal. To use that same concept in a retail environment. Those of you that are in the Android world, we have full sets of plugins for all of the Ant Plus device profiles. We have an Ant USB service when you can connect with an OTG cable to any cell phone that's got 4.1 Android or higher. As I said, we have many of the new cell phones that are coming out with Ant built in, so that Ant service is already built in, but you can download the service for a non-built-in phone from the Google Play. There's the plugins that I talked about. Again, these plugins allow you to be able to ask simply for what data you want. If you want to get heart rate, you don't have to set up a channel. You just have to ask for it. So on an app environment, it makes it so much easier to create an interoperable app. And it's 100% guaranteed to be interoperable because of the plugin. So in summary, no single protocol will be the best at everything. We're not capable of doing everything. Zigbee, Bluetooth, Wi-Fi, everybody's got their goods and their bads. We expect that you will be looking for extremely low power and simplicity when you're making your decision. We do that extremely well. We give you the chance to be able to start off with a simple solution and expand that solution not with hardware but with simple application code. Many of the applications for an Ant Plus device profile are less than 100 bytes. And then ANT enables a very much more complex and powerful use cases, as you've seen, not just a simple star like some of our competitors.